Hello everybody, welcome back to our channel EASI. Everything about semiconductor industry or everything that you need to know about semiconductor industry. Today we are going to talk about GPU or the graphics processing unit, which is the engine that is powering the modern computing. So let's get started. What is a GPU? A GPU is a specialized processor designed for massively parallel computation. Though originally it was built to render graphics, it is now a cornerstone of AI, scientific computing, and data centers. A modern GPU contains thousands of small cores designed to execute thousands of threads simultaneously. They were built to process the millions of pixels and vertices needed for real-time 3D rendering in video games and visualization, and the same architecture that renders pixels is perfect for matrix maths, which is the backbone of neural network training and inference today. GPUs now power hyperscale data centers, thus driving the AI revolution at a planetary scale. How is a GPU different from CPU? Let's compare GPU and CPU at different matrices to understand it better. Cores. CPUs have less number of cores but large and complex, while GPUs have thousands of small cores but they are simple. When goal of CPU is to minimize latency for sequential tasks, that of GPU is to maximize throughput of parallel tasks. CPU operates at 3 to 6 GHz while GPU operates around 1.5 to 2.5 GHz. CPUs have large caches but GPUs have smaller caches per core. CPUs work with lower bandwidth of memory while GPU with high bandwidth memory like HBM. CPUs are best for OS, databases, branching, while GPUs are good for graphics, AI, and scientific simulations. With lower amount of parallelism for CPUs while massive parallelism for GPUs. Now let's talk about GPU performance metrics. Key metrics for evaluating GPU performance include flops for compute power, memory bandwidth for data throughput, and thread count for parallelism. What is a teraflop? Teraflops measure floating point operations per second, the key metric for GPU compute power. High memory bandwidth enables rapid data transfer between GPU cores and RAM. Modern GPU supports thousands of concurrent threads for massive parallel computing. One of the examples of GPU is NVIDIA's flagship RTX. GPUs excel at the parallel matrix computation that forms the backbone of machine learning algorithms. Their thousands of core processes vast amounts of data simultaneously, reducing training times from weeks to hours and thus enabling real-time AI interface at scale. Therefore, facilitating neural network acceleration, high parallelism for matrix operation, and scalable deep learning pipelines. The key players of GPUs are NVIDIA, dominant in AI due to CUDA ecosystem, NVLink, and first mover advantage in deep learning. AMD, strong in HPC with growing AI presence, open source ROCm gaining adoption. Intel, which is re-entering discrete GPU market where Gaudi targets AI interface cost efficiency. Despite rapid advancement, GPU development faces significant technical and market hurdles that shape the industry's evolution, like power consumption and heat dissipation, Modern GPUs push thermal limits with power draws exceeding amount of wattage, requiring advanced cooling solutions. Manufacturing complexity and cost. Manufacturing at cutting edge nodes like 4 nanometer and below demands precision and drives cost higher. It requires a continuous software optimization with competition with specialized AI accelerators. So with that, we have come to an end to today's session. Please like, share and subscribe. See you next time. Till then, stay safe and stay healthy.